This is CSAT Sample Test 4, Question 11. We are given a binary tree with n levels, as in this figure. On each level, we draw a line passing through all nodes on that level, horizontally, like this. Part A asks us what is the total number of triangles formed in this way. Think about how you would approach this. If you haven't tried it yet, pause the video now and try working your way through the question. Then resume when you've made an attempt. One way we might want to start dealing with this is to work it out for small numbers, such as n is 1, 2, 3, etc. We may spot a pattern, in which case we can guess a formula and prove it by induction. Instead, we could try calculating it directly. There's no guarantee that guessing a pattern will work. So let's see if we can calculate this directly. For example, if we pick a particular node, how many triangles is it in? Let's start by looking at our diagram. For this top node, which triangles do we have? We have one that goes down to level 2, and we have another one that goes down to level 3. We'd have another that goes to level 4, and so on. Let's think a bit more about putting a number on this. If we know how many triangles a particular node forms, then we can add up all the nodes in the graph to get our final answer. So, what would this number be? For each node, the same as on our diagram before, we have one on the level below, one on the next level, and so on, as many levels as we have left. If we're on the kth level, how many levels are there below that? Since there are n levels total, there are n minus k levels, and hence a node on the kth level is at the tip of n minus k triangles. How can we add this up over the whole graph to find the number of triangles? How many nodes are on each level? How many levels are there? Our first level has one node, and each time we go down a level, we double it. So, what must our number of nodes per level be? Level k must have 2 to the k minus 1 nodes, and hence we can add up, for each row we have 2 to the k minus 1 nodes times n minus k triangles formed by that node. So now we have an expression for our number Tn, the number of triangles. We just need to evaluate this sum. So how can we begin to evaluate this sum? First, I think it might be a good idea to separate these two terms, since n is just a constant and k is not. So we can split this sum into these two distinct parts. Let's consider each of these sums separately, and then subtract them at the end. Do you recognise the form of the first one? Is it something we can deal with easily? Let's think about the first one separately. Hopefully you will have noticed that this is a geometric series with common ratio 2. We have a general formula for the sum of a geometric series, given here. So, multiplying by n still, and substituting into our formula, we get that the sum of this is n times 2 to the n minus 1 all over 2 minus 1. Since 2 minus 1 is just 1, we multiply out this bracket to give n 2 to the n minus n. Next, we need to deal with this other sum. You may know a formula for this, but if not, I'll show you a useful method to evaluate a formula like this. Let's think about where to start. Does this term look familiar to you? k, 2 to the k minus 1. It almost looks like something's been differentiated. If 2 were replaced by x, this would be the derivative of x to the k. Let's consider that sum, and see if we can then differentiate to find our result. By using our geometric series again, we find the sum from k is 1 to n of x to the k is x to the n minus 1 over x minus 1. We can bring the x inside the fraction to give x to the n plus 1 minus x all over x minus 1. Now, let's write down what we said before about differentiating this sum. Differentiating each term separately, we get the sum from 1 to n of kx to the k minus 1. How can we use this to evaluate our sum in the red box? We have another expression for the sum, so let's differentiate this form. We'll do this by the quotient rule, since we're differentiating a fraction. You should memorize the quotient rule. Writing out the form, we get u dv by dx minus dv by dx u all over v squared. We could now try and simplify, but in fact we know that what we're going to do is substitute in x equals 2, which will simplify this a lot without us having to do anything. So let's move straight ahead to that step. Substituting, our term here now becomes our term in the red box. The sum from k is 1 to n of k 2 to the k minus 1. Since now 2 minus 1 is 1, we can ignore our denominator. This term x minus 1 will also be 1. So substituting in, we get n plus 1 lots of 2 to the n minus 1 minus 2 to the n plus 1 plus 2, where two negative signs make a plus. Expanding out this first bracket gives us n 2 to the n plus 2 to the n minus 2 to the n plus 1 plus 1. Now, adding this to the term from our blue box, we get n 2 to the n minus n from our blue box, minus the terms we just found from the red box. Notice that these two terms are the same, with a change in sign, so we can cancel these. Can we simplify what we have left any further? In fact, 2 to the n plus 1 minus 2 to the n will just give us 2 to the n. To see this, you can factor out 2 to the n, giving us 2 to the n times 2 minus 1. This is similar to how binary numbers work. So if you're familiar with those, this should be an intuitive result. Then, since 2 minus 1 is just 1, we can write Tn equals 2 to the n minus 1. There are other ways to get to this result, some of which I'll discuss in the next part. Part B asks us to give a recursive expression for this number. What does this mean, a recursive expression? This means we want to find something like Tn plus 1 is some function of Tn. Remember that we found an expression for Tn already. So, one way to find a recursive expression is to find Tn plus 1 by substituting in, and then converting some of the terms into the form something Tn. Let's see what we can do. Expanding out Tn plus 1, we get this form. We want to relate this to Tn, so we want to see a 2 to the n rather than a 2 to the n plus 1. Let's also rearrange our constant while we're moving things around. This gives us 2 lots of 2 to the n minus 2. To me, this looks almost like 2 lots of t to the n, except we're missing an n term. So, what we can do is write it as 2 lots of our expression for Tn, and then add our missing n term at the end. Now we can rewrite the bracket as Tn, and we have a recursive expression. Tn plus 1 equals 2Tn plus n. There's more than one recursive expression of this form, and there's more than one method to get to it, but I think this is the easiest method. Let's consider an alternative method. This one can be used in the first part to find your answer without going through all the difficult sums. Let's think about our tree with n levels. How can we construct a tree with n plus 1 levels? If we took 2 copies of this tree and put them side by side, and then added an extra node to the top, this would make an n plus 1 tree. When we think about adding a level to our n-leveled tree, we might think to add it to the bottom, but in fact, it makes more sense to add it to the top, since then we only deal with the one extra node. The construction would look like this. We take our 2 n-leveled trees, and then connect them at the top by our extra node. Now, is there any easier way to think about the number of triangles, particularly in terms of the number for n levels? We know that we'll have all the same triangles in each of these 2 n trees, plus however many we get from our top node being added. How many will we get from our top node? Remember, in the very first part, we looked at one single node and counted how many triangles it formed. In fact, we have one for each level going down, so an extra n. And hence, once again, we get our recursive expression, Tn plus 1, the triangles in an n plus 1 leveled tree, is twice the number from an n leveled plus n. The reason this might be useful for the first part is that we can find this relationship without knowing what Tn is. If you're good at solving recurrence relations like this, you will be able to find Tn from this formula. Even without finding it exactly, you could guess a similar formula. For example, 2 to the n plus an plus b, and solve for a and b, hence giving your answer. So this is a useful way to look at the first part of the problem as well.